Welcome, my name is Matthew, and in this video we're going to talk about the law of sines. And the law of sines is pretty straightforward, actually. I don't think this is going to be too tricky, except under one set of circumstances. And we'll look at those together, and we'll look at each of the different ways that that one particular set of circumstances can go. Let's have a look. So we could be talking about the law of sines as pertains to a right triangle, I suppose, although it's a little bit overkill for a right triangle. We could be looking at an obtuse triangle, as you're seeing on the right, or we could be working with an acute triangle on the left, but really, the law of sines is most useful when we are working with a triangle that's not a right triangle, which makes it an oblique triangle. So oblique triangles do not contain a right angle. And here's the law of sines. The law of sines is made of these three fractions, except we're only ever going to use two of them at a time, and I'll show you what I mean. Here's a little space for us to do a proof, but I'm not going to spend time in this video proving the law of sines to you. What I want to do is go into this example, and I want to, well, actually, right before we do that, I want to point out that there are certain cases or sets of circumstances that we use the law of sines. I don't commit these to memory, and as we go through, I will tell you, especially once we get to the law of cosines, I'll tell you about how it is that I remember, or actually I don't ever remember which cases sort of compel me to use the law of sines versus law of cosines. Basically, I look for one kind of a marker, and if that's present, then I know to use the law of sines. And if it's not there, then I'm stuck using the law of cosines. But in this case, it's here, and the thing that's here, side angle, 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 side angle, and side angle. Those are the three situations where we would want to use the law of sines. And it's hard to tell from that, the first one has two angles in it, the second one has two angles in it, but the third one has two sides and one angle in it. So what is it that they have in common that would compel me to use the law of sines? Here's what they have. This is angle A, and this is side A. And you'll notice that angle A and side A are across from each other. So are side and angle C and side and angle B. Angle measures are typically labeled with a capital letter. Side lengths are labeled with a lowercase letter. So that sort of general pattern holds true in this diagram. And what you see here is that we know angle A, and we know its corresponding side length A. And what I'm going to do is I'm going to refer to that as a pair. In order to use the law of sines, we're always going to need a full pair of information, either A and A, B and B, or C and C. What we're going to solve for is the missing element in this pair. We only have one of two elements in that pair, and so we're going to solve for the other one. So we've got an A and a C, and we're missing a C. And so if we come back up to the law of sines, we have this value, we have this value, we have, I think it was angle C, yep, and we're going to be solving for side C. So we only have one unknown, but we're only going to need to use this fraction and this fraction. We don't need to use the one in the middle because we're not working with angle B yet. So let's give it a shot. Let's get rid of all of these circles. There we go. Okay, so also, sorry, I know I'm jumping around a lot here in the beginning. Let's see, let's use m divided by n equals d over e. When you have a fraction equal to another fraction, and it's something as simple looking as this, you're allowed to take the reciprocal of both sides of the equation. So I could rewrite this. That's a sort of a double-sided arrow that I just drew very poorly there. I could rewrite this as n over m equals e over d. So you're allowed to flip both sides of the equation, but only when you have a fraction equal to a fraction. And we're working with this fraction and this fraction, so if for some reason I wanted side c to be in the denominator at the outset of working one of these problems, I could sort of restructure this equation and take the reciprocal, and I could write sine a over a equals sine c over c. Some of you will become comfortable enough with this information and this topic and this process, and you'll have the insight and you'll think to do that at the beginning of a problem. Some of you won't, and that's okay. You'll just take the reciprocal of both sides of the equation later instead of at the beginning. I don't need to do it in this case, so I'm going to write lowercase a over sine a equals lowercase c over sine c. A little bit difficult to distinguish the c's from each other, but that's okay as long as we're plugging the correct information into the right spot. So side length a is 16, and you're going to need a scientific calculator or graphing calculator for this process. If you don't have it already, go get it. The sine of 33 degrees. We are in degrees here, so make sure your calculator's in the right mode. We don't know side length c yet, and in the denominator is the sine of 128 degrees. Now I like to get this equation what I call calculator ready. I like to do all of my arithmetic that I can with paper and pencil before I start plugging into the calculator, and the only thing I need to do in order to solve for c here is to multiply both sides of my equation by the sine of 128. So if you want to write out all of that arithmetic, you're welcome to. You could write the 16. I'm going to write it out so that for those of you who want to have absolutely every ounce of your work shown, it will be here for you. And for those of you who don't need to write out this additional step, that's fine. I'm going to multiply this side by the sine of 128, and I'll multiply this side also by the sine of 128. What we do to one side, we do to the other. And we did that so that these would cancel out, leaving us just with that c value in the numerator. And so we have gotten our equation calculator ready. Let's just write this out one more time. Not a sine of 133, just the sine of 33. There we go. Okay, so now I'm going into my calculator. Which one should we use? Let's start with the graphing calculator. It's so easy to punch this in. I want to get you an answer to this one as soon as possible. I'm going to hit the mode button for starters and confirm that I'm in degree mode, and I am. The mode button's near the top left corner of your keypad. I'm on a TI-84 Plus. So I'm in degree mode, so I'll hit second quit in the top left corner there. And then I'm going to type this equation in almost exactly as it appears. I'll hit sine, which gives me a parenthesis automatically, 128, and then I need to close my parentheses, and then times 16, and then divided by sine again, 33. You can close your parentheses or not right there at the end, but I'm going to close them and hit enter. And I got an answer of 23.14959. So I'm going to round it to 23.15, I think. So that's my C value. Let's go back and look at our diagram real quick. We did not know the measure of side B. We didn't know side C, and we didn't know angle B. So we have found one of our sides, and we'd like to find the measure of our other side now. So let's see if we can do that. Well, I know that we can, I just don't know that I did all of this work in a very convenient spot on my paper to allow me to have enough room in order to solve for side B. I might have to go into the margin a little bit over here, but I think it'll work. Okay, so in order to find the measure of side B, oh, I can't find the measure of side B unless I know angle B. In order to find side B or angle B, I would need to know one member of that original pair. So to find side B, I need to know angle B. To find angle B, I need to know side B. I wonder if we could find side or angle B first. Oh, we can, because we know that a triangle has 180 degrees in it. I know what the other two angle measures are, so we can do some subtraction and solve for angle B. I'm going to do that over, let's see. Trying to decide where I've got more room. I think I'll do my subtraction over here. So let's write ourselves a little note. We've got one, how do I want to do this? Let's say angle B equals 180 minus angle A minus angle C. Okay, so that's equal then to 180 degrees minus 33 degrees minus 128 degrees. And you should know by now that I'm not the king of arithmetic. So for arithmetic, I do go into my calculator. That's not the mistake I want to make. Minus 128, and it's 19 degrees. That looks pretty accurate. Angle B is pretty small. A little degree symbol on there. Okay, we've got our third angle, and then let's use that nice round number of 19 degrees in order to find side B. Sort of block this area off over here. I'll be better organized on the next problem. I gotta get into the rhythm of these problems. So we're solving for side B, so I'd like side B to be in the numerator, so I'm going to put that over the sine of angle B equals, and then we're going to need a full pair. So we already know that I might come into my diagram and write in that 19 degrees. There it is. I have half of this pair now, that's good. And then I need to use a full pair. We could use angle C and side C as our full pair, except the side length that we have, 23.15 for side C, is a rounded value. And I'd rather use something that's precise. And we were given that side A is exactly 16 units, whatever it is, centimeters, inches, feet, miles, don't know, but it's exactly 16. So I'm going to use A and A again. So let's put our lowercase a up here and the sign of capital A in the denominator. You'll notice the side lengths have to be consistently in the numerator and the angle measures in the denominator, or if you flip both of these fractions, angles on the top, sides on the bottom. Okay, let's plug in some information. We don't know side B, so I'll keep the B there. Sine of 19 degrees, we determined that, equals side A is still 16, and it's the sine of angle A is 33 degrees. And we need to solve this equation. Let's get it calculator ready, solve it for side B. I'll multiply both sides by the sine of 19. I'm not going to show my work this time. You already know how to do that. We're multiplying both sides by the sine of 19. And we get 16 times the sine of 19 goes into that numerator. The sine of 33 is still in the denominator. I tried to make that 19 look more like a 19. I'm not sure if I succeeded or not. There we are, and we're calculator ready. Let's go into the calculator. This time I'm going to try to do this in my scientific calculator, which is always a little bit more of a challenge. I'm using a single line entry calculator, which is the TI-30XA. It's got this one's got a green second button up here in the top left corner. Some of these also have a yellow second button, so that's sort of an indicator of which one you're using, but it's the TI-30XA, and this calculator has a button right next to that second button in the top left corner that says DRG. And if you keep pressing that thing and looking at your screen, you'll notice something changes. It goes from rad for radians to grad, and then if you hit it again, it goes to DEG for degrees. And we want to make sure that we're in degree mode. So now that I'm there, I'm going to type this, the right-hand side of this thing in a very unusual way. If you're not very good at typing this in yet, you might actually want to write down the keystrokes for being able to type this in and practice it to make sure that you're able to do this on a quiz or in a test situation. So I'm going to type in 19 and then hit the sign button. And then I'll hit times 16 equals, and here's where it gets weird, divided by, I just hit the divided by button, then type in 33, hit the sign button, and on your screen right now it says 0.5446 blah blah blah. That's just the sine of 33 degrees. The division of the numerator and denominator has not happened yet. We need to hit equals. There we go. Now the division has been performed, and I got a final answer of 9.56. It's rounded to 2 decimal places. 9.56. Not much of a 5. Those are all of the missing values from the triangle that was given to us. We were given 2 angles and we had to find one of them. We were given one side and had to find 2 of them. So that's 3 pieces of missing information. We've got them all. This is not my best presentation of work, but we did manage to get it all to fit on one page. I hope you did too. And we can now go in to try another problem. This problem is actually very similar. It's just a different situation where we're being given some different starting information, question mark. It's a little bit different. In this problem that we just did, we were given 2 angles and a side. In this problem, we're being given 2 angles and a side. In this problem, the 2 angles that we were given, in a way, you could say that side B is between those 2 angles, A and C. And we didn't know B. So we were considering that we were given A and C. The other piece of information that we were given was a side length that was not between the angle measures. In this problem, however, we are being given a side length that's between the 2 given angle measures. So it's a little bit different scenario, but it doesn't change our approach very much. The first thing that you might want to do in this space over here is 180 minus 82 minus 54. That will give you the measure of angle A. Not only will it give you the measure of angle A, but then you'll have a full pair. And you will then want to use A over the sine of whatever that found angle measure A is, and you'll set it equal to lowercase b over the sine of B, which is 54 degrees. So fill that information in and then march through the process, which is only a couple of steps, just like we did a couple times in the previous problem. That's going to help you find the measure of side B, and then, and you won't be able to fit all that work into here probably. You might have to come up into here and finish it here. And then in the remaining space that you have, I would recommend using A and A again. And you'll be looking for side C this time. So there's our C. We know what angle measure C is. It's 82 degrees. So in that denominator, you'll have the sine of 82 degrees. You'll know this piece of information. You'll know this one. You'll know this one. And you'll be looking for this one. Go through those motions and see if you come up with some side lengths that seem reasonable to you. Based on this diagram, which looks like it's pretty close to drawn to scale, don't ever assume that it's exactly drawn to scale, but in this one it looks pretty close to being drawn to scale. Let's see, just real quick. 180 minus 82 minus 54 is 44. So angle A is your smallest angle measure, which means it must be across from the smallest side, 16. Now 54 degrees is just slightly larger than that. So side B should be slightly larger than 16. And side C is across from an angle measure that is, well, you might say substantially larger. 82 compared to 54 degrees, that's quite a bit larger. So side C should be the longest of your side lengths. If I had to guess, maybe side B is going to be around 18, and maybe side C is going to be around 22, something like that. So you see how the larger side should be across from the larger angle measure. See what you get, and if you're one of my students and you work that through and you find that you have questions on it, or you're getting side lengths that are strangely large or strangely small, let me know and we can look at that together. But what I'd like to do is to continue moving on into this, because this I think is where we need to spend even more time together. This is called the ambiguous case, and the ambiguous case happens under this one set of circumstances where you're given a side, and then an angle measure that's not between those two sides. And in these four diagrams, you're seeing which sides were being given. Sides B and A, those are the only ones labeled in those diagrams, and the only angle measure that's present there is angle measure A. Now this is just an example. You could be given sides A and C and angle measure C. But what's consistent is this pair. Right, this is a pair of values. The A and the A are across from each other. Could be C and C, could be B and B, we don't know. But we're going to need to have that information, so that's one of the sides and the given angle measure. Another thing that's characteristic about the way that these diagrams are drawn is that the bottom side of the triangle, which in this case is side C, is being drawn horizontally. And I use this analogy where I talk about a ramp. You could think of it as a skateboard ramp or a bike ramp or I don't know, whatever other kind of ramp you want. But a ramp is something that maybe when you were a kid, you built on the ground and you made it out of some 2x4s and a piece of plywood or something. I don't know. Or maybe you were just ramping off of the side entry to a sewer grate or something like that. I know I did that when I was a kid with our little BMX bikes. So this is what I consider to be the ramp. In this diagram, that's side B. So if I'm riding my bike, I'm coming in from over here and I'm going to hit this, I'm going to go up here and go flying off of this ramp. We're not going to do that. We won't be on any bikes. The other thing in this diagram, other than the ramp, is this part, which is what I call the ground. That's the horizontal element, and it's horizontal because I grew up in Florida where the ground is actually flat and sort of horizontal. And then the A value, this side length over here, is what I'm going to call the rope. I'm going to go through some diagrams where instead of riding my bike up here, I'm going to walk up to the top of this ramp, and I'm going to drop a rope off the edge, and that rope sometimes is going to come all the way down and reach the ground. Sometimes it'll come down and I'll have some extra rope on the ground. Sometimes the rope's not going to quite reach the ground. So these are the different scenarios that we're going to be working with. Let's look at an example. So here we've got side-side angle, and I'm going to try to draw my diagram pretty much the same for all of these problems. My angle measure is A, so I'm going to draw one side of my angle here, and I'm not going to draw the other side here because angle A is 150 degrees. That's not a 150 degree angle. So I have to draw the other side of my angle measure, maybe something like this. And I haven't even looked at side lengths yet. All I've done so far is to try to make this look like 150 degrees. Okay, so this is angle measure A, and side A is going to be across from angle measure A. So really side A is hopefully going to be over here. So if you drew all of that, hopefully you drew it with pencil, because some of it you're going to have to modify. We also need to talk about side B. Now, in the diagrams that we saw above, right below where I am in the top left corner, you see this, oops, hold still. You see this side length B right here? That means that across from it is angle B. So I'm going to pretend, again, that angle B is down here in the bottom right corner in our diagram that we're drawing. And this should have side length 10, based on what was given to us in the problem. And side length B is going to be 30. And it's a little tough to tell because this triangle is quite skinny. This is side length B, and that measures 30. Now, if I drew my angle measure fairly accurate at 150 degrees, it looks like 15 with a little, I don't even know what that little symbol would be next to it. Can I erase that? There it is. If that 150 degree angle measure is pretty accurate, and then I've got this side length of 30, let's say that that's accurate. Based on the side of that side length of 30, does this 10 look like it's about a third of the length of the 30 unit long side? I don't think so. Side A is supposed to be shorter than side B. Except if I drew side A shorter than side B, a third the length of it, in fact, it would be about this long. It's not going to be possible for us to close the triangle with the given information. With a 150 degree angle measure and one side length of 30, this other side length of 10 that we're talking about is not going to facilitate a triangle, which is why this problem says solve the triangle if possible. This one is not possible. So this is a graphical or diagrammatic or picture way of illustrating, literally illustrating to you, that it's not possible for us to solve this triangle. Let's see if we can do this with a more trigonometric way, an arithmetic way. Let's use math to show that this triangle is not possible. I've drawn my diagram, and it's pretty clear to me that it's not possible, but maybe it's a free response question and I have to actually demonstrate that. So let's see if we can do that. We were given angle measure A and side A, so we have this as the full pair, and then we were given side length B, which means we should try to find angle measure B. So we could write ourselves a little note here, maybe find capital B. Let's find angle measure B. Okay, so do I have enough room to do this? I'm going to start all the way in the margin because I think I might need to. I've got lowercase a over sine A equals, now here's a scenario. We're solving for capital B. So I'd like to put capital B in my numerator. So I'm actually going to write my formula sort of this time as the sine of A over A equals the sine of B over B. That way that angle measure B is already in the numerator. That's the thing that we're looking for. Okay, so the sine of angle, so sine of 150 over side A was 10 equals the sine of angle measure B. I don't know what B is yet, so we'll just leave it as a B. Divided by the given side length of 30. There we go. And now, in order to solve for angle measure B, the first thing I need to do is multiply both sides by 30. I need to get this denominator of 30 away from the right-hand side of the equation. So I'm coming up here. Multiplying both sides by 30 gives me 30 sine 150 degrees divided by 10 equals sine B. And finally, using paper and pencil, in order to isolate our B value on the right-hand side, we need to take the inverse sine of both sides of the equation. So I'm going to write it. It's going to look a little messy, but this is, I think, what has to be done. We're taking the inverse sine of 30 sine 150 degrees, all divided by 10, and that's equal to angle B. Make sure your calculator is still in degree mode, and let's see what we get for angle measure B. I'm going to use my graphing calculator because it's so much easier to type it in. I'll try to go back and forth between calculators. So I'm hitting the second button, the sine button, which puts a little inverse sine on my screen. 30 times sine 150. Now this calculator automatically puts in some parentheses. So I have to close the parenthesis at the end of the 150. And now I'm going to hit divided by 10. And then I'm going to close the parenthesis after the 10. And I think that ought to do it. 30 sine 150 divided by 10, all inside the inverse sine. Yep. I'm going to hit enter. And I get error domain, which means that I've just tried to take the inverse sine of something that's not in the domain of the inverse sine function. I wonder what it was. I'm going to go back to, so I selected go to as the option on that error message. I'm back on the home screen of my TI, and I'm going to scroll back over and delete this inverse sine thing at the beginning of my statement. And I'm going to delete the parenthesis at the end. So now I just have 30 sine 150, where the 150 degrees is still in parentheses, divided by 10, enter, and I get 1.5. Let's actually write that into these notes. Now I drew this diagram in kind of an inconvenient location. I wish that I could cut this part of my diagram, cut it and paste it over here so it's not in my way anymore. I'll find different software one day which will allow me to do that. But for the moment, oh, it's just terrible to have to do that. Let's see, I don't want to do that. I want to do just one arrow here and say that this is equal to the inverse sine of 1.5 is equal to B. Now, what's the domain of the inverse sine function? The domain of the inverse sine function is the same thing as the range, vertically, of the original sine function. And the range of the original sine function goes from -1 to +1, right? That's our curve that goes up and down between negative and +1. But this number 1.5 is not between negative and +1. So we should write a note that says not in domain of inverse sine, therefore, whether you spell your therefore with an E at the end or not, I think it can be spelled both ways. Therefore, how did the question, not possible, I suppose we could say. You could say no triangle, no solution. But that would be the sort of more mathematical way of proving or demonstrating that this triangle cannot be solved. You should go through the motions on that next one and see what you can see. The diagram is going to be fairly similar, except the side lengths are a little bit closer to each other. The angle measure is even more extreme, so that's going to be a tough triangle to draw. You might want to draw the triangle not to scale, just to give you a little bit more room to work. You could still label this appropriately as the 162 degrees, except you'll use a pencil that you're actually capable of writing with, not like me with this digital pencil. And label your diagram nicely, so that's the A. Oh no, I don't like this at all. I'm not adhering to my my structure that I like. Let's draw it like this, because I want to have this horizontal side that represents the ground. This is sort of my ramp, although that would be tough to ramp because you'd be like climbing backwards. But this is still angle A. This is 162 degrees. And side length A is 6.1. And I typically take the B value and put it over there because I was given side length B, which is the 4. So you've got your full pair, and you've got a half of a pair with the angle B, which is unknown, and the given side B, which is 4. So you can use this exact same setup that we started with that's right here and go to town. And my hope is that this value right here is going to be between -1 and +1. Well, it's not going to be negative, so something less than 1, so that you can actually take the inverse sine of it and find angle measure B. Then you'll know angles A and B, and you can do subtraction to find angle C. And once you've got angle C, you'll have the half of a pair necessary to find side C. I just realized, actually I've already made the next video that comes after this, but the next thing that you're going to watch and take notes on is this problem where we talk about the ambiguous triangle, where you're going to be given some information like this, and the result is going to be possibly 2 triangles. And in order to determine for certain that there are 2 triangles that you need to wrestle with, we're going to have to do a little bit of trig, and it's going to be very easy. And then this very meticulous process of going through the 2 different possible resulting triangles is what we're going to go through. And it is long and tedious and time consuming. So if you think maybe you need a break before we move into that next part of this set of notes, take a break. Eat a little something, get hydrated. If you maybe want to take a little 20-minute power nap, now would be a great time to do it. And then after working on that problem, you might need another little power nap. All right, so get yourself into the right state of mind. Make sure that your pencil is sharp. Grab a glass of water or something caffeinated maybe, and then click on that link that's right there, and I will see you for the ambiguous triangle.